Hello, it's stat134, lecture 22. Next Wednesday you have quiz 4 covering sections 4.1 and 4.2. Last time we started the exponential distribution. So the exponential distribution is the time until the first success or arrival and has density f of t is lambda e to the minus lambda t when t is positive. And the probability that t is between 0 and 0 plus dt here, which is the shaded region in the picture below. So this is f of 0 dt. F of 0 is the height at 0, and dt is the width. So this is lambda e to the minus lambda times 0 dt, which is just lambda dt. So lambda is the probability that that your arrival is in dt divided by dt. So you can interpret that as the instantaneous rate of success. Now the exponential has the memoryless property. It's the only continuous distribution with a memoryless property, and that says that the probability that t is in dt, given that t is greater than t, is just the probability that t is between 0 and 0 plus dt. So in this picture here, I've shown that the chance that your arrival comes after time t in a small interval of time dt is exactly the same as the chance that the arrival comes just in a small interval dt after 0. So you can confirm that here just using Bayes' rule. And the interpretation here is that so long as a light bulb is still functioning, it's as good as new. In other words, lambda doesn't change. So we often model mechanical devices according to failure of mechanical devices according to a exponential distribution. We also showed that if x is geometric p, that px, that change of scale, converges to exponential 1 as p goes to 0. What we're going to do today is the expectation invariance of exponential lambda, as well as the gamma distribution. So the expectation invariance of the exponential is quite easy to calculate just using the definition. I've written out the steps using integration by parts at the end of these notes, and you should take a look at that. But in essence, the expectation of t is 1 over lambda. The variance of t is 1 over lambda squared. And you can check this for lambda is 1. If you recall that if x is geometric p, the expectation of x is 1 over p, and the variance of x is q over p squared. And the expectation of px then is p times the expectation of x, which is 1, which goes to 1 as p goes to 0. So now px goes to exponential 1, and hence the expectation of px goes to the expectation of t as p goes to 0. So the expectation of t then is 1, which makes sense since the expectation of t we just said was 1 over lambda, and lambda is 1. So good. Furthermore, you can also check that the variance of t is 1 here. Just follow the reasoning as shown. So the interpretation of lambda, it gives us an interesting interpretation of lambda because the expectation of t is 1 over lambda. Lambda is 1 over the expectation of t. So you can interpret lambda as 1 over the average time of arrival. So for example, if t is the waiting time in minutes until a blue Honda arrives at a toll gate starting at noon, the waiting time is on average 2 minutes. Find the probability that t is greater than 3. You would write the expectation of t is 2 minutes, so hence lambda is 1/2 minutes, inverse minutes. So in other words, on average, half a blue Honda comes every minute, and t is then exponential 1/2 inverse minutes, or probability that t is greater than 3, just use your exponential formula. So next we're going to discuss the gamma distribution. So a gamma distribution, t has two parameters, r and lambda, where r is a natural number and lambda is some positive constant. Yes, and so this is a sum of r IID exponential lambdas. So we write t is w1 plus ... wr, where these wi's are exponential lambdas. And so I just made a picture here. Imagine I have time here, and the x's represent arrivals of something, and these occur at times t1, t2, t3. So t1 is gamma 1 lambda, t2 is gamma 2 lambda time to the second arrival, t3 is gamma 3 lambda. W1, W2, W3 are all independent exponentials, just the inter-arrival times. So now let's see here. We can describe the gamma r lambda as the time of the rth arrival in a Poisson process. So let's remind ourselves what Poisson process is. So n sub t is Poisson lambda t. So here lambda is our rate per unit time for t amount of time. So that's the average number of successes occurring in time t. And the probability that nt is n is given by the Poisson formula. So, for example, let t be the waiting time in minutes until a blue Honda enters a toll gate starting at noon. The waiting time is on average 2 minutes. Find the probability 3 blue Hondas arrive in 8 minutes. So lambda is a half blue Hondas per minute. So n sub 8 is Poisson 8. It's Poisson 4. 4 is 1/2 times 8. So probability that n sub 8 is 3 is e to the minus 4 cubed over 3 factorial, just from the Poisson formula. So let's go back to the gamma distribution now. So say that n sub t is Poisson lambda t and w is exponential lambda. So the probability that t is in dt means that I get r minus 1 arrivals before time t, and I get 1 arrival in dt, a small time after t. So probability that t is in dt is the probability that nt is r minus 1. I have r minus 1 arrivals by time t, times the probability that I have a 1 arrival in dt. So w is in dt, and exponential is in dt, given that w is greater than t. And you can just write out what these things are, and we can derive here the density for gamma. Now, this formulation for the density of gamma is in terms of a Poisson process here, and so r is necessarily a natural number, but the gamma distribution generally is defined for r any positive real number. So let's talk about that for a minute. I'm going to define this thing called a gamma function in this special case when r is a natural number to just be r minus 1 factorial. And in that case, my density has this form, and here the constant parts have no t in it, and the variable parts have t in it. When I integrate this, of course this integrates to 1 because it's a density. I can solve for gamma t and get this formula. So this is actually the definition for the gamma function. And using this definition, if r is a positive integer, you can prove using induction that gamma r is r minus 1 factorial. So so we can define the gamma distribution for r positive as what's written here. So now suppose that t is gamma, r is 4, lambda is 2 inverse seconds. You can calculate what the density is. Just follow your formula. Furthermore, if t is gamma r lambda, the probability that t is greater than t, that's the integral from t to infinity of your density. And in a picture, what that is it is the chance of getting less than or equal to r minus 1 arrivals before time t. Yeah, that's what it is. So so the probability that t is greater than t is equal to the probability that nt is less than or equal to r minus 1. So this is a huge idea here. It just makes it so much easier to calculate than solving the above integral there. So we'll definitely do it this way. So we can just use our Poisson formula here for all the different values of that nt can take between 0 and r minus 1. So we just get this sum here. So for example, if t is gamma, r is 4, lambda is inverse 2 inverse seconds, the probability that t is greater than 7, so let's find that. And so the probability that t is greater than 7 is the probability that n sub 7 is less than or equal to r minus 1. R here is 4, so that's 3. And so I just use my formula here, and I get my answer. And the probability that t is less than 7 is 1 minus the above answer. Finally, another problem here. Suppose customers are arriving at a ticket booth at a rate of 5 per minute according to a Poisson arrival process. Find the probability that starting from time 0, the 9th customer doesn't arrive within 5 minutes, and at least one customer arrives within 40 seconds after the arrival of the 13th customer. Well, the probability that that t is greater than 5 is just the probability that n sub 5 is less than 9, or less than or equal to 8. So here n sub t, or n sub 5 is Poisson 25, 5 times 5. And furthermore, by the memoryless property, after the 13th customer, you can just think of that as an exponential. So W14 exponential there, being less than 2/3, we have to convert seconds to minutes, is just 1 minus the survival function. Okay, so have a great weekend, and I'll see you next time.